Applications of derivatives. In the previous lesson, we learnt how to find the derivatives of various types of functions. In this lesson, we are going to learn applications of derivatives. There are many applications of derivatives. Here is the list of some of the applications of derivatives which we are going to learn in this lesson. Rate of change of quantities, increasing and decreasing functions in intervals, tangents and normals, errors and approximation, local maximum and minimum value of the functions, and absolute maximum and minimum value of the functions. Let us learn one of the applications of derivatives, which is rate of change of quantities. Consider an example of price of tomatoes per kg. We say rupees 50 per kg. So here the price of the tomato depends upon the weight. As the number of kgs will increase, the cost of the tomato will increase. Similarly, as the number of kgs are decreasing, the cost of the tomatoes will decrease. Let us consider ds by dt, where s is the distance travelled by a particle and t is the time taken. So, rate of change of the distance s with respect to time gives the velocity. Similarly, dv by dt, that is rate of change of velocity with respect to time, gives the acceleration of the particle. So, in general, let us consider y as a function of x. So, as x changes, y is going to change. X is called an independent variable and y is a dependent variable. So, as x changes, y also changes. Let us consider that x changes from x to x plus h, where h is a very small increment. Therefore, y also changes accordingly. The amount of change in y is given as f of x plus h minus f of x, where h is a very small positive quantity. Now, the average rate of change is given by f of x plus h minus f of x divided by x plus h minus x, which is f of x plus h minus f of x divided by h, that is change in y value divided by change in the x value. Now, the rate of change of y with respect to x is given as dy by dx, which is limit h tending to 0 of f of x plus h minus f of x divided by h. And the instantaneous rate of change of y with respect to x when x is equal to x0 is given by dy by dx at x is equal to x0, limit h tending to 0 of f of x0 plus h minus f of x0 divided by h. Now, let us consider that both the variables x and y are changing with respect to another variable t. That is, y is a function of t and x is also a function of t. Now, in this case, to find dy by dx, we have to apply chain rule. First, y has to be differentiated with respect to time t, and then t has to be differentiated with respect to x. So that dt and dt will get cancelled, we will get dy by dx. Or we can write this as dy by dt upon dx by dt. We are getting this result by applying chain rule. dy by dx may be positive or negative. dy by dx will be positive if y increases as x increases or y decreases as x decreases. that is x and y are directly proportional to each other, and dy by dx will be negative if y increases as x decreases or y decreases as x increases. That is, x and y are inversely proportional to each other. The rate of change of quantities application includes acceleration and velocity in physics, population of growth rates in biology, and marginal cost and marginal revenue in business and economics. Before we start the exercise, we should be thorough with the mensuration formulae of two-dimensional and three-dimensional figures. Let us see some of them. First one, circle. Area of a circle is pi r square, perimeter of a circle is 2 pi r, where r is the radius of the circle. And second one, square. Area is a square, perimeter is 4a, and length of the diagonal is a root 2, where a is the side of the square. For rectangle, area is L into b, perimeter is 2 times L plus b, and diagonal of the rectangle is root of L square plus b square, where L is the length of the rectangle, b is the breadth of the rectangle. Then for triangle, area is half BH or half AB sin theta, where theta is the included angle between the sides A and B. Equilateral triangle, area of an equilateral triangle is root 3 by 4a square and height is root 3 by 2a, where a is the side of the equilateral triangle. Then area of a trapezium is half h times a plus b, where a and b are the lengths of the parallel sides, h is the height of the trapezium. Then area of the parallelogram is BH, where B is the base of the parallelogram, H is the height of the parallelogram. Now we will see the formulae for some of the three-dimensional figures. Cube, volume of a cube is a cube, lateral surface area is 4a square, and total surface area is 6a square, and diagonal of the cube is a root 3, where a is the side of the cube. Cuboid, volume of the cuboid is LBH, lateral surface area is 2h times L plus b, and total surface area is 2 times LB plus BH plus LH, and diagonal of a cuboid is root of L square plus b square plus h square, where L is the length, b is the breadth, h is the height of the cuboid. Next, cylinder. Volume of the cylinder is pi r square h, curved surface area of the cylinder is 2 pi r h, and total surface area is 2 pi r into h plus r, where r is the radius of the cylinder and h is the height of the cylinder. Cone. Volume of the cone is 1/3 of pi r square h, curved surface area is pi r l, total surface area is pi r into L plus r, and the relation between r, h and L is L square is equal to r square plus h square. They form a Pythagorean triplet. Sphere. Volume of a sphere is 4 by 3 pi r cube, and surface area of the sphere is 4 pi r square, where r is the radius of the sphere. Hemisphere. Volume of the hemisphere is 2 by 3 pi r cube, curved surface area is 2 pi r square, and total surface area is 3 pi r square, where r is the radius of the hemisphere. Exercise 6.1. The first question. Find the rate of change of the area of a circle with respect to its radius when r is equal to 3 centimeters and r equal to 4 centimeters. Here we have to find the rate of change of area of the circle with respect to its radius. Let r be the radius of the circle and a be the area of the circle. Area of a circle formula is pi r square. Now we will differentiate with respect to r. So we get dA divided by dr equal to 2 pi r. Now we have to find the instantaneous rate of change of area with respect to the radius. We have to find dA by dr when r is equal to 3 centimeters, which is 2 pi into 3, 6 pi. The unit for dA by dr will be, area unit is centimeter square and radius unit is centimeters. Similarly, dA by dr, when r is equal to 4 centimeters, 2 pi times 4, which is 8 pi, and the unit is centimeter square per centimeter. The values which are given in the question should be substituted after differentiation, not before differentiation. Second question, the volume of a cube is increasing at the rate of 8 centimeter cube per second. How fast is the surface area increasing when the length of an edge is 12 centimeters? We will take x, v and a as the side, volume and surface area of the cube. Now, after defining the variables, we will write the given quantities. The volume of a cube is increasing at the rate of 8 centimeters cube per second. From the unit, we can make out that it is dV by dt because it is per second with respect to the time. How fast is the surface area increasing? We have to find dA by dt. When the length of an edge is 12 centimeters, the given values should be substituted after differentiation. So, volume of a cube formula is x cube. Let us differentiate both sides with respect to t. We get 3x square into dx by dt using chain rule. dv by dt is given as 8. 3 times x square is 12 square times dx by dt, from which we can get the value of dx by dt. 8 divided by 3 times 12 into 12. 1 divided by 54, and the unit is, side unit is centimeters and time unit is seconds. We have to find dA by dt. Surface area of the cube, we will take the total surface area 6x square. Now let us differentiate both sides with respect to t. dA by dt is 6 times 2x into dx by dt. Now we will substitute the given values. X is given as 12 and dx by dt is 1 by 54. The answer is 8 by 3, and the unit for dA by dt, area unit is centimeter square and time unit is seconds. So, centimeter square per second. Therefore, the surface area is increasing at the rate of 8 by 3 centimeter square per second. Question number 3. The radius of a circle is increasing uniformly at the rate of 3 centimeters per second. Find the rate at which the area of the circle is increasing when the radius is 10 centimeters. We will first define the variables which we are going to use. R and A are the radius and area of the circle. Now we will write the given quantities. The radius of a circle is increasing uniformly at the rate of 3 centimeters per second. Look at the unit, 3 centimeters per second. That means it is with respect to time t. And the radius is given as 10 centimeters. Find the rate at which the area of the circle is increasing. We have to calculate dA by dt. Area formula is pi r square. Let us differentiate both sides with respect to t. dA by dt is 2 pi r into dr by dt, chain rule. Now we will substitute the values which are given. 2 pi, r is 10, dr by dt is 3 centimeters per second. Therefore, the answer is 60 pi, and the unit for dA by dt is centimeter square per second. Therefore, the area of the circle is increasing at the rate of 60 pi centimeter square per second. Fourth question, an edge of a variable cube is increasing at the rate of 3 centimeters per second. How fast is the volume of the cube increasing when the edge is 10 centimeters long? We will take x as the edge and v as the volume of the cube. The edge of the cube is increasing at the rate of 3 centimeters per second. dx by dt is 3 centimeters per second. How fast is the volume of the cube increasing? We have to find dv by dt when the edge is 10 centimeters long. These given values should be substituted only after differentiation. Volume of a cube formula is x cube. We will differentiate both sides with respect to time t. dv by dt is, on the other side we have to apply chain rule, 3x square times dx by dt. Now let us plug in the values which are given. 3 times x square is 10 square times dx by dt is 3, which is 900, and unit for dv by dt is centimeter cube per second. Therefore, the volume of the cube is increasing at the rate of 900 centimeter cube per second. Question 5. A stone is dropped into a quiet lake and waves move in circles at the speed of 5 centimeters per second. At the instant when the radius of the circular wave is 8 centimeters, how fast is the enclosed area increasing? So if a stone is dropped into a quiet lake, ripples will be formed. So r keeps on increasing and area of the circle also keeps on increasing. R and A be the radius and area of the circle. Now we will write the given values. The waves move in circles at the speed of 5 centimeter per second. Look at the unit, 5 centimeters per second. That means it is dr by dt. And when r is 8 centimeters, how fast is the enclosed area increasing? Area of the circle formula is pi r square. We will differentiate both sides with respect to t. dA over dt is 2 pi r times dr by dt. Let us substitute the values which are given. 2 pi, r is 8, dr by dt is 5. 80 pi, and the unit for dA by dt is centimeter square per second, which is a positive quantity. Therefore, the area of a circular wave is increasing at the rate of 80 pi centimeter square per second. Question 6. The radius of a circle is increasing at the rate of 0.7 centimeter per second. What is the rate of increase of its circumference? R and C we will take. Let R be the radius and C be the circumference. Let us write the given values. The radius of a circle is increasing at the rate of 0.7 centimeter per second. 0.7 centimeter per second is dr over dt. What is the rate of increase of its circumference? We have to find dc over dt. The circumference of a circle formula is 2 pi r. Let us differentiate both sides with respect to time t. dc over dt is 2 pi into dr by dt. We will substitute the value of dr by dt, which is 0.7. The answer is 1.4 pi. Circumference unit is centimeters and time unit is seconds. Therefore, the rate of increase of its circumference is 1.4 pi centimeter per second. Question 7. The length x of a rectangle is decreasing at the rate of 5 centimeters per minute. It is given that it decreases. Therefore, dx by dt should be taken as a negative quantity. and the width y is increasing at the rate of 4 centimeters per minute. When x is equal to 8 centimeters and y equal to 6 centimeters, find the rates of change of the perimeter and the area of the rectangle. Let A and P be the area and the perimeter of the rectangle. The first subdivision, rate of change of perimeter. Perimeter of a rectangle is 2 times x plus y, where x is the length and y is the width. Let us differentiate both sides with respect to t. dp by dt is equal to 2 times dx by dt plus dy by dt. Let us plug in the values which are given. Dx by dt is minus 5, don't forget this negative sign, plus dy by dt is 4. The answer is minus 2, and perimeter unit is centimeters, time unit is minutes. And it is negative. Therefore, the perimeter of the rectangle is decreasing at the rate of 2 centimeters per minute. If we write the word decreasing, we need not write the negative sign in the answer. Now the second subdivision, we have to find the rate of change of area of the rectangle. Area of the rectangle is length into breadth. Let us differentiate both sides with respect to time t. dA by dt is equal to, we will use product rule here, dx by dt into y plus x into dy by dt. Let us plug in the values which are given. Dx by dt is minus 5, y is 6, plus x is 8 and dy by dt is 4. The answer is 2, which is positive. Therefore, the area of the rectangle is increasing at the rate of 2 centimeters square per minute. Question 8. A balloon which always remains spherical on inflation is being inflated by pumping in 900 cubic centimeters of gas per second. Find the rate at which the radius of the balloon increases when the radius is 15 centimeters. Let R and V be the radius and volume of the balloon. (900 cubic centimeters per second). So this is dV by dt. Find the rate at which the radius of the balloon is increasing when the radius is 15 centimeters. Volume of the sphere formula is 4 by 3 pi r cube. Let us differentiate both sides with respect to t. dV by dt is 4 by 3 pi. We have to apply chain rule to differentiate r cube. Power has to be differentiated first, then the base r has to be differentiated with respect to time t. So 3r square times dr by dt. Let us substitute the values which are given. 900 is 4 pi, r square is 15 square times dr by dt, from which we can get the value of dr by dt. 900 divided by 4 pi 225. 4 times 225 is 900. The answer is 1 by pi centimeters per second. Therefore, radius of the balloon is increasing at the rate of 1 by pi centimeters per second. Question 9. A balloon which always remains spherical has a variable radius. Find the rate at which its volume is increasing with the radius when the latter is 10 centimeters. We will define the variables which we are going to use, r and v, radius and volume of the sphere. The volume is increasing with the radius. The radius is given as 10 centimeters. We have to find the rate at which its volume is increasing with the radius. Differentiation has to be done with respect to r. Volume of a sphere formula is 4 by 3 pi r cube. Let us differentiate with respect to r. dV by dr is 4 by 3 pi 3r square. And r value is given as 10 square. The answer is 400 pi. Unit for dV by dr, volume unit is centimeter cube and radius unit is centimeters. Question 10. A ladder 5 meters long is leaning against a wall. The bottom of the ladder is pulled along the ground away from the wall at the rate of 2 centimeters per second. How fast is its height on the wall decreasing when the foot of the ladder is 4 meters away from the wall? The length of the ladder is given as 5 meters. We will take the distance between the wall and the ladder as x meters and the height of the ladder on the wall as y meters. We will take it as A, B, C. AB is y meters and BC is x meters. If the foot of the ladder is pulled away from the wall, x increases. When the bottom is pulled away from the wall, the height of the ladder on the wall will decrease. Y decreases. And it is given that the ladder is pulled away from the wall at the rate of 2 centimeters per second. dx by dt is 2 centimeters per second. And we have to find dy by dt. And foot of the ladder is 4 meters away from the wall. X is 4 meters. We need a relation between the variables x and y. So we are going to use Pythagoras theorem. X square plus y square is equal to 5 square. Now let us differentiate both sides with respect to t. 2x times dx by dt plus 2y times dy by dt is equal to 25 is a constant, derivative is 0. We can divide throughout by 2. We have to substitute the given values. We can calculate y when x is 4 meters. Y square is 5 square minus 4 square. 25 minus 16 is 9. Therefore, y is 3 meters. See the unit. X and y are in meters, but dx by dt is given in centimeters per second. We can change the unit. Even if we don't change the unit, we will get the same answer because of the ratio. We will change the unit to centimeters. This is 400 centimeters. This is 300 centimeters. 400 times 2 plus y is 300 times dy by dt equal to 0. Therefore, dy by dt is minus 800 divided by 300. The answer is minus 8 by 3. Therefore, the height of the ladder on the wall decreases at the rate of 8 by 3 centimeters per second. If it is mentioned decreases, we need not write the negative sign. Question number 11. A particle moves along the curve 6y equal to x cube plus 2. Find the points on the curve at which the y coordinate is changing 8 times as fast as the x coordinate. The y coordinate is changing 8 times as fast as the x coordinate. So, dy by dx is given as 8, or you may use dy by dt is equal to 8 times dx by dt. Now, let us differentiate this equation with respect to x. 6 times dy by dx is equal to 3x square. and dy by dx is given as 8, 3x square, x square is 16, therefore x is plus or minus 4. If x is plus 4, we will find y by substituting it in the given equation. 6y is 64 plus 2, which is 66, y is 11. Therefore, the point is 4, 11. If x is minus 4, 6y is minus 64 plus 2, which is minus 62. Therefore, y is minus 31 divided by 3. The point is minus 4 minus 31 divided by 3. Therefore, the points are 4, 11 and minus 4 minus 31 over 3. Question 12. The radius of an air bubble is increasing at the rate of half centimeter per second. At what rate is the volume of the bubble increasing when the radius is 1 centimeter? We will take r and v as radius and volume of the bubble. Volume of the sphere is 4 by 3 pi r cube. We will differentiate with respect to t. dv by dt is 4 by 3 pi. We have to apply chain rule, 3 r square times dr by dt. 4 pi, r value is 1, 1 square is 1, dr by dt is half. The answer is 2 pi and the unit for dv by dt is centimeter cube per second. Therefore, the volume increases at the rate of 2 pi centimeter cube per second. Thirteenth question. A balloon which always remains spherical has a variable diameter 3 by 2 times 2x plus 1. Find the rate of change of its volume with respect to x. So, we have to find dv by dx. We will take r and v as radius and volume of the sphere. Volume of the sphere formula is 4 by 3 pi r cube. We will substitute for r. Diameter is 3 by 2 times 2x plus 1. Therefore, radius will be half of it, 3 by 4 times 2x plus 1. Therefore, v is 4 by 3 pi r cube, 3 by 4 times 2x plus 1 the whole cube. 4 by 3 pi, 27 divided by 64 times 2x plus 1 the whole cube. Therefore, v is 9 over 16 pi 2x plus 1 the whole cube. Now, let us differentiate with respect to x. 9 by 16 pi, power has to be differentiated first and then the base. 2 times derivative of x with respect to x is 1 and derivative of 1 is 0. The answer is 27 over 8 pi times 2x plus 1 the whole square. Therefore, the rate of change of its volume with respect to x is 27 over 8 pi 2x plus 1 the whole square. Question number 14. Sand is pouring from a pipe at the rate of 12 centimeter cube per second. The falling sand forms a cone on the ground in such a way that the height of the cone is always 1/6 of the radius of the base. How fast is the height of the sand cone increasing when the height is 4 centimeters? As we keep pouring sand, the radius, height and the volume of the sand cone will keep on increasing. Let r, h, v be the radius, height and volume of the sand cone. 12 centimeter cube per second is dV by dt. We can make out from the unit. Centimeter cube is volume unit and height is given as 4 centimeters. We have to find dH by dt. And it is given that h is 1/6 of r. Therefore, r will be 6 times h. Volume of the cone formula is 1 by 3 pi r square h. H is given, we need dH by dt, but r is not given and dr by dt is also not given. So, let us eliminate r from this. Pi by 3 times r is 6h, 6h the whole square times h. Pi by 3 times 36h square into h. 12 pi h cube. Now we will differentiate with respect to t. dV by dt is 12 pi times 3h square times dH by dt. Let us plug in the values which are given. 12 is equal to 12 pi times 3 times h square. H square is 4 square 16 times dH by dt. Therefore, dH by dt is 1 divided by 48 pi and the unit is centimeters per second. Therefore, the height of the sand cone increases at the rate of 1 divided by 48 pi centimeters per second. Question number 15. The total cost C of x in rupees associated with the production of x units of an item is given by C of x is equal to 0.007 x cube minus 0.003 x square plus 15x plus 4000. Find the marginal cost when 17 units are produced. X is given as 17. We know that the marginal cost is dC by dx, which is equal to, let us differentiate and write 0.007 times 3x square minus 0.003 times 2x plus 15 plus 0, which is 0.021 x square minus 0.006 x plus 15, and the value of x is given as 17. We will find the instantaneous rate of change of C. 0.021 17 square minus 0.006 times 17 plus 15. 17 square is 289 times 21. The answer is 6.069 minus 17 times 6, 0.102 plus 15. 6.069 plus 15 will be 21.069 minus 0.102. The answer is 20.967. Therefore, the marginal cost is equal to rupees 20.97. We are rounding it off to 2 places. Question 16. The total revenue in rupees received from the sale of x units of a product is given by R of x is equal to 13x square plus 26x plus 15. Find the marginal revenue when x is 7. We know that the marginal revenue is dr by dx. Let us differentiate and write 26x plus 26, and we have to find dr over dx when x is 7 units. 26 times 7 plus 26, it becomes 26 times 8, which is 208. Therefore, marginal revenue is rupees 208. Next question, choose the correct answer in exercises 17 and 18. Question 17, the rate of change of area of a circle with respect to its radius at r is equal to 6 centimeters is. Area of the circle is pi r square. Let us differentiate with respect to r. It is 2 pi r. R value is given, which is 6 centimeters. Therefore, the answer is 12 pi. B is the correct option. Question 18. The total revenue in rupees received from the sale of X units of a product is given by R of X is equal to 3x square plus 36x plus 5. The marginal revenue when X equal to 15 is. We know that the marginal revenue is dr by dx. The differentiation is 6x plus 36. Now we will find dr by dx when x is 15. 6 times 15 plus 36. 90 plus 36, 126. D is the correct option.